Today, ladies and gentlemen, we are going to be going over my pre-calculus MT4 project, by me of course, over polynomials, zeros, solving for them, graphing them, and verifying their plausibility using a very fun theorem, which we'll talk about later. For this video and for the remainder of this presentation's purposes, we're going to be focusing on these four main zeros: -6, -1, 3, and 6. The first thing we're going to want to do with those zeros is put them into a factored form. If you're given zeros, you want to put them into a factored form if you're going to be expected to graph it. That is kind of basically saying that we're just going to be setting each of these equal to x, and then each of those equations trying to solve to get it to equal to 0. You might be saying, is this just speaking gibberish right now? What's going on? This is all I'm saying is, if we're going to use 6 for example, if 6 is one of our zeros, that basically is just saying that x equals 6. And to get it into a factor form, we need it to equal 0. So if x equals 6, to get that equal to 0, all you would do is subtract 6. So x minus 6 equals 0. That's how we get this number. And you would just do the same for the remainder of the zeros, which in this case is +3, -1, -6. Just remember, in factored form, the sign's always opposite of the sign that it is when it's not, when it's just in your base 0. What's in factored form is just opposite next to an x. And if you have like an imaginary solution, those always come in pairs. That's always important to keep a reminder of. I don't use any for this purpose, but just remember, if you have like an imaginary solution like 3 plus I, it wouldn't just be 3 plus I, it'd be 3 plus I and 3 minus I, because they always come in pairs. But we don't gotta worry about that, because from this, we're gonna do something that when you see it, you might get jump scared. So brace yourselves. This is gonna be our base polynomial, or what most people call it, the standard form that comes after the factored form. You might be saying to yourself, how the heck did he get that from a bunch of numbers and x? Very simple. This entire thing maybe takes, if you're inexperienced, 5 to 10 minutes to get. You might be saying, that's impossible. I need a degree in physics, I need a degree in everything. This is impossibly hard. It's not really as hard as you think. All you have to do, or what I do at least, is you take 2 of these, so I like to basically split it down the middle, pair these two together, and FOIL them. FOIL means first, inside, outside, last, and that is basically just how you're going to distribute. So I'm closer here, so I'm just going to use x minus 3 and x minus 6. All you do is distribute the x to the other x squared, x to the -6, -6x, x to the -3, -3x, and then -3 to the -6, which is plus 18. So this would just be x squared minus 9x, because you combine like terms, plus 18. For one side, you do the same in the other. And now you're saying, okay, I have these two. Now what I do? You do the same thing again, but this time with slightly bigger equations. It's not as hard as you think, as long as you stay organized and you remember your steps, remember to FOIL correctly. You should end up, after combining like terms, an equation like this. Now that we have our standard form polynomial, what we want to do with this is we want to graph it to visually see what this equation looks like. So the easiest thing to do when you have a standard form polynomial and you're asked to graph, what you should get correct on every single test is your y-intercept. Now you might be saying, okay, why are you pointing at this number? What's so special about this 108? I'll tell you. When you're solving for a y-intercept, what you're gonna do, because this entire thing is y equals this equation. When you want your y-intercept, what do you want to set all your x variables to? 0, right? Because you want it to be on that y-axis. So if these can't be equal to anything, they have to be equal to 0 if you want the final point to end up on your y-axis. And now you might be thinking, okay, so now why 108 my y-intercept? That's because if you replace every single one of these numbers with 0, this is just the same as 1x to the 4th. every number that's in front of each of those variables will be being multiplied by 0. And as we know, according to the 0 property, any number multiplied by 0 is equal to 0. So your y-intercept is always going to be the remaining number that does not have a variable. Always. That's the same if it was x to the 22nd power plus 432 x to the 21st, yada, yada, yada. If it ends with like plus 42, that 42 would be your y-intercept, or in this case, 108. It's simple. Just look at the last number that doesn't have a variable. That's y-intercept. Now, arrow directions on both sides. This is saying that, like, okay, the furthest line on the left is going to end like this, or start if it's on the left. It'll look like this. And the furthest side on the right line will look like this. That may sound confusing, and it might just sound like I'm talking gibberish. I kind of am, I'm kind of not. Bear with me. When determining the sides of our graph. So, the most important, we already have one point in the graph, the y-intercept. That's a point. It's not a solution, which we already had. The zeros are also points. I'll get to them in a minute. But this is how, like, you wouldn't just draw points on a graph, connect them with a line, and just have no arrows. You'd have arrows on each side, pointing like, okay, it's going to continuously grow in this direction. That's what these are. And the reason we know that both sides are going to point up and are both going to be pointing slightly up and out is because it's a positive, even equation. Now, I'll give you a second. You can pause the video if you want to figure out why it is that. Got it? If not, I'll show you why. The reason it's an even solution and why one of the sides is up, in this case left, is because of this 4. The degree to which you take it, whether it's even or odd, determines the value, the side. Now, it's a good idea to get a base understanding of x squared kind of looks like a U, negative x squared looks like a frowny face, and then like x cubed, for example, looks like a, it's kind of hard to describe it, but it's like up to the right and up continuously, and then negative x cubed is down to the right, slightly down, and then straight down. Kind of like a lightning bolt, I'd say. Just remember that. But x to the 4th is going to be the same as x squared. Since it's a positive, even solution. Remember, even because the degree is 4. Positive because we're going to imagine that there's a 1 out in front of that x to the 4th. And that 1, since there is no negative sign, is positive. And since it's a positive even, both sides will go up. Simple as that. So now you have at least one point. We'll get to the rest in a minute. And you have how it's going to end. So right now you could kind of plot it. But that x to the 4th, that 4 right there, is how many zeros you have. And unfortunately, we, as of now, would have 0 points because if our y-intercept is 108 and these lines start like this, we were just going to draw it, it wouldn't cross over the x-axis at all. You don't have 0 points, we have 4, which means we're missing some, which are these. These are going to be our points along the x-axis. Now, hopefully I'm not getting too boring right now. I know it's math, and some people are like, yeah, math, I hate this. This is actually kind of cool. So, those points that we started with, that got us to this main equation, don't mind me, all of these points that I started with, these come into play. Each one of these are going to be placed along the x-axis. So now you're thinking, wait a second. He said that if it's to the 4th degree, you need 4 solutions. And a solution is where it crosses the x-axis. And these 4 points show where it crosses the x-axis. We have all 4 points and our y-intercept and how it's each side is going to end. We can graph it. You gosh darn right we can. There's our final graph. We can see that both of the sides, I use Desmos by this, it's a great website, I would highly recommend. We can see that both sides end going up, which we determined by looking only at the first variable. That simple, determine the majority of the graph. Then we can see that each one of these along the y-axis, each one of these cubes goes up by 50. And that's kind of hard to tell, but it goes 0, 50, 100, 150, 200. If you can't see it, that's my fault. But the y-intercept, it's kind of hard to tell, but it's right above that 100, right at where that 108 would be. That's our y-intercept, so we can verify that, which we solved for right here. Remember, just looking at one number. So far, we looked at two numbers, and we have a majority of our graph. Now, we're going to look at these numbers. -6, -1, 3, and 6. Now, the numbers on the x-axis go by increments of 2, so each cube is a 2. So I'll be looking, hey, it's not a whole number. It is, just trust. Okay, so we know that's increments of 2. So if we go in the negative direction, we know one of our furthest 0 to the left is -6. So we go -2, -4, -6. That's 1. That's good. And then we know that one's -1. Well, 2, if it's by increments of 2, it has to be half of 2. So, if -1 is half of 2, it'd be right in the middle of that box, which it is. And then we have 3. I'll just go back so you can remember them. We did these two. Now it's time for the positive ones, 3 and 6. Now, half of 3 is 1.5. So we go over 1.5 blocks in this case. There's one block. There's half of the second block, which is where it crosses. And then the last one is right on the money with 6. So there's our final graph. Now, I want to go over a very important thing. I talked about imaginary solutions, but I want to talk about solutions that have a second degree. So let's say, for example, we have these 4, but I'm going to add a hypothetical one. Let's say we hypothetically add another 6. In that case, instead of crossing at 6, it would bounce off at the 6. You see what I mean? So instead of crossing it where it's at the 6 right here, it would actually like just touch the x-axis at the point, and it would go straight back the way it came. And that would completely change the ends of the graph, because we would have a 5th solution, which would make it an even odd, which would make it look like, so it would go down, up, down, and then back down. So, but that's not this equation that we need to worry about. This is the one we need to worry about. This is our final graph. If you can get this, great job. You did amazing. But now, this is the final thing. We're going to be verifying our solutions and making sure that we can, in fact, have, if I go back, 2 real negative solutions and 2 real positive solutions, which we can clearly see here. We do this through Descartes' rule to verify the number of zeros, as I like to say, or Descartes' equation, or his theorem. He's a very cool guy, actually. Highly recommend you maybe Google it, give him a quick little Google, look him up. He invented this thing that's actually really neat. So basically, the way it works is, I'm going to look at the positive ones for now, or the possible real solutions, and how I got 2 or 0 possible positive real solutions. That is, it's kind of unique in a way, because what you do is very simple. You look at where the sign changes and how many times that occurs. So, in this case, the x to the 4th, remember how we said it was positive? And notice how this minus 2x to the cube is negative? That is one sign change. Remember that. And we kind of skip over, and then we can see, hold on, it goes from negative 39x squared to positive 72x. That's a sign change. That's 2. So you might be thinking, oh, 2 positive solutions. No. We have to take into account imaginary solutions. And as we know, imaginaries come in pair. So what you do is you take the number that you found originally and you subtract 2. So 2 minus 2 is 0. So it can be 2 or 0. Because there is a possibility that there is an imaginary solution and no positives. But in this case, we know there is, because we have the zeros. So the answer is 2 or 0 possible real positive solutions using Descartes' rule. But we did that for the positive number of zeros. Now we got to do it for the negative. For the negative, all you do is you're flipping signs, but you have to do it very specifically. Once you understand, it's not confusing. But if you mess up, it will kind of screw up your answer, which is not good, because this is how we are verifying that we can have 2 positive and 2 negative solutions that are real. What you do is every number or every coefficient that has a variable to the degree of an odd number. What I mean by that is because this is the negative thing. So you think negative, okay, we just flip all the signs. Wrong. Like that x to the fourth, since it's to the degree of 4 and 4 is an even number, we leave it alone. But you can tell that this 2x to the third right here turns into a positive 2x to the third from a negative because this 3 is an odd. It's to the degree of an odd number. That is the only time you flip it. So we're thinking, okay, x2, that's an even number. We'll leave that. But you're thinking, okay, x. X is the same as x to the first. 1 is an odd number. We should flip that. You're correct. This goes from positive 72x to negative 72x. And since 108 doesn't have anything, you don't got to worry about it. That stays the same. So we do the same thing. Positive to positive. No, that's not a sign change. Don't worry about it. Positive to negative, 1. We skip over negative to positive. That's 2. So we have 2. And remember our thing of subtracting 2 to factor in imaginary, but we still keep the original. So 2 or 0 negative real solutions. There. We basically just verified that we can have 2 negative real solutions, right here, -6, -1, and 2 positive real solutions, 3 and 6, using Descartes' rule. Thank you. I hope you enjoyed this project. Make sure to like and subscribe. Peace.